or hit record. Let me share screen again here. So back to the PowerPoint. So that's what they're talking about when they're saying that the tolerance zone is the space between two parallel planes. So it's two parallel planes, in this case, that are 0.2 millimeters apart. The tolerance zone may be oriented to best fit the high and low points of the surface, which we talked about, where it can shift up or down. But all surface elements of the controlled surface must be within this zone. And then we can't forget about the rule number 1 as well, too. Feature of size, so what's the difference? So on a feature of size, the flatness tolerance may be larger than the feature of size dimension tolerance. And that's because here we're talking about maximum material condition as well, we get a bonus. The distance between the planes is equal to the flatness tolerance value. And the derived median plane must be located within the tolerance zone. So let's go back to the whiteboard and talk this through a little bit, because this gets to be a little bit more difficult to comprehend, especially kind of first time around thinking this stuff through. So again, same part, drawn out, 3D. They called out a tolerance, or what was the size of that thing? I like to forget that too. Let me go back and double check that.
4, I think.
4, was it? All right, thank you. As they keep bouncing around, we're going to get seasick, changing screens all the time. So if we called out a dimension of 4.0 and then attached the GD&T to it, flatness of 0.2 to that 4.0, let's go back to our front zone, or front view of the drawing. We all remember before where that flatness tolerance box looked like. It somewhat straddled this face a little bit. Now we're going to change it up with the feature of size tolerance zone, because if you remember from when you take your drawing class or any blueprint reading, let's draw what a center line would look like on here. That's a horrible center line. Let me redraw that. That would represent the center line of the two faces. Our tolerance zone from a feature of size standpoint is now like this. And how do you measure the flatness of a theoretical feature? Becomes a bit more different. Now what they're measuring is at every point along this 3D part, and again, I apologize for my horrible drawing, definitely not the scale. The center point of every location from here and here has got to lie within that box. So if the top of the part was a little more wavy, looked like this, for some reason, it got bent for whatever reason, the center point from these two areas would fall right here, which is outside of that tolerance zone. So from a feature of size standpoint, this part would be rejected.
So you would definitely use a max inscribed instead of a best fit on your CMM.
Sorry, say that again, Francis?
That means you would definitely use a max inscribed instead of a best fit when you're creating that feature on your CMM.
Could be probably a bit advanced for what we're trying to talk about today, though. Francis is talking about some of the CMM programming that we can do.
Oh, the max inscribed would give you the fattest result, where the best fit gives you an average of all the points.
Okay. All right. Let me stop this, go back to PowerPoint. So that is how we talk about feature of size flatness tolerances rather than, I'm not sharing my screen here. There we go. So feature of size versus a surface tolerance from a flatness perspective. Any questions on flatness before we move forward?
Is flatness called out separate from a standard control box, or is it all called out in the same box, in a dimensioning box, or and is it called out alone?
As far as you're talking about like what I'm circling right here, this feature control frame.
Yeah. So if you had a measurement going there for deal, and then flatness it was a piece of that part, do you call that out in a separate box beside that, or is it called out in the same box?
I'm not sure I'm 100% understanding, Dave. So if you're in the case of this dimension right here, this 4.2.
Right. So let's say that you wanted that to be 8 inches plus or minus, or 8 whatever plus or minus 10,000, right?
Okay.
And you made that, you put that was in a feature control box because it does have a center line, it does, and it meets that requirement. Would the flatness be in a separate box off to the side?
And
Or would it group it together?
Size, where it calls out the size of something, doesn't appear in the feature control box. It's the other things that modify that particular feature, like location or something. Is that what you're trying to say? Location would appear in the same box as flatness?
But okay, so if you were to take the drawing that we had, the other problem 5, and you had that, you had the as you saw in there, some of those deals had dimensions plus or minus 8, plus or minus, 2, whatever it was.
Mm-hmm.
Is flatness called out separately, or is it included in one of the same boxes?
It's typically called out separately. So, and again, really the main difference is where the location of the tolerance is pointed towards. So if it's a surface, right, it looks like it's hanging out all by itself. It's in a whole different area of the drawing, whereas you can pull it off of an extension line and it looks like it's attached to the dimension as well too, or you can actually attach to the dimension as well. But I think if you look at this example right here, Dave, you can see that the thickness is not in a box itself, but the dimension itself is below it. And I did open up my book to page 62, and I'm looking at the dimensions here, and I can see what you're saying. There's a flatness on one side of that part. It is off all by itself, but there is a length dimension associated with that surface or that feature of the part. So that flatness and that length tolerance both apply to that feature of the part, but they're located separately on the drawing.
So that flatness applies across the entire surface of that.
Yep.
So if you sweep it with an indicator, it should be within tolerance, or it's not a good part.
Exactly.
Or with a CMM or whatever you're going to use to measure it.
No, exactly. You're exactly right. So it applies to the entire feature. The only time there are times where, let me create a share for you as well too here. There are instances where you can take a flatness tolerance, and let's say you've got a feature of part here, a size, same part that we're looking at. This 4.2. If you applied a tolerance, there are times where you can create a zone within that tolerance, within the whole face, and have the flatness apply to only the area within inside that zone as well too. So you start to see that in the industries that Scott Forge works in, where the parts are absolutely gigantic. 100,000 pound components that are going to fit into other assemblies, but not the entire face of the part is going to be touching with something else in the assembly. So to try and hold that tolerance across the entire face is not cost effective. So what they'll do is they'll add in dimensions on the part and say, only for this 2-inch by 1-inch box that's located a 1/2 inch in from the corner, you have to hold that flatness in, because that's going to be the only area that makes contact with something else during the assembly. So without that box created, and you'll see that in a handful of different ways. Some people might cross-hatch that box and say within this area. Without that box or some other defining feature, you will assume that it means for the entire face.
Okay.
Perfect. Keep doing it. Back to the. Keep going to the PowerPoint without hitting share first. It doesn't work for you guys, and you can't see it. All right, here we go. Squeeze back over. So the next tolerance that we want to talk about is a straightness tolerance. Very, very similar to a flatness tolerance. So, think of the things we were just talking about with flatness, and we're going to apply it a little bit differently here for the straightness tolerance. So straightness is defined in the specification as a perfect line. It applies to a surface or to a feature of size, dimension. So same thing, just like a flatness tolerance would. Can also apply to a center line or a derived median line of a part. As we get through a lot of this GD&T, you'll start to see a lot of similarities, a lot of the same nomenclature used between all these parts or all these tolerances. So what are the tolerance zone shapes? So if a flatness tolerance zone was the space between two planes, the tolerance zone for a straightness is the space between two parallel lines. The space between the lines is the straightness tolerance value. It can also be the space within a cylinder. So the size of a cylinder is the straightness tolerance value. And we'll talk about that a little bit more here moving forward too. So again, rule number 1 applies to straightness just like it does to flatness. You cannot take a part feature and make it greater than the actual tolerance size of the part. So you can't say that it's within tolerance because one end of the part is at the high limit and then it gets tapered out and the line is not straight, and the left side of the part becomes larger than the dimension size of the part. That violates rule number 1, and that part is out of tolerance at that point. Different modifiers that can be used for straightness tolerance. So you see we're building on some of the ones we talked about earlier. We added a new one. So the tolerance modifier is a diameter symbol, and that is a cylindrical feature of size, which we'll talk about here. I'll give some examples for that as well too. Again, the F for releasing the restraint requirements. Not super common. Maybe it is for some of others, depending on the industry. Me working in the metal industry, there's not a lot of non-rigid components that we're seeing. ST for statistical process control. Those that took the quality class with me last semester got a introduction to statistical process control, but typically defined in other areas on the blueprint via notes or possibly in the inspection requirements, not typically in the GD&T feature control frame. And then we see our modifiers for maximum material condition and least material condition as well. So again, the beautiful thing about those is they permit a bonus tolerance. We're not going to get into bonus tolerances tonight, but we'll start talking about those as we get a little deeper into some other GD&T features. So starting to see the similarities of how tolerances are applied. Here we're looking at 2 different ways we can apply a straightness tolerance. The one on the left side is how you can apply straightness directly to a surface. And on the other side is how you can apply it to a feature of size. And we'll talk about the differences of these too. So looks very identical to the flatness, right? Here they're pointing it towards the edge of the part of the surface, or they're using an extension line to pull it off of the surface itself. The feature control frame on this side, where they're attaching it to the dimension, means it's applied to the feature of size. Same thing here, check. Check for datums, assess the application, review the modifiers, and evaluate the tolerance. Where do we want to use straightness at? Or why would we use straightness? For a lot of the same reasons that we would use flatness. So support, so equal load along the entire line element. Path of motion, you want the same contact on a straight track or rail. You want the parts to assemble properly, and sometimes to reduce the manufacturing costs. Straightness tolerance to surface is the tolerance zone between two parallel lines. The straightness tolerance only applies in the view which it's shown, and the tolerance zone extends across the entire length of the surface. We'll talk about through examples here. Let's go back to that drawing. So let's go to whiteboard and we'll show this drawing right here. Double check on my size, it's 12.2. So if I go to recreate drawing in my beautiful handwriting here. Oops. We have our diameter part. Diameter is 12.7 to 12.2. I apologize, it won't let me put my hand down on the whiteboard on my iPad, otherwise it starts leaving marks. So my handwriting is pretty rough. So if we called out a straightness tolerance, oops, let me redo this feature control frame here. Call out a straightness tolerance on that surface of 0.2. What our tolerance zone looks like is two straight lines that are 0.2 millimeters apart from each other. The entire surface of that line has got to fit within between those two parallel lines. So again, if this part was wavy, it's okay as long as that waviness is between those two parallel lines. If any point of the waviness pops outside of that, then because of that one area right there, this part is no good. So it doesn't take much to make the entire part out tolerance. Again, with a part like this, you could fix it more than likely. Any questions on that straightness tolerance? Back to the PowerPoint. Associated with the feature size dimension. Oh, I'm not, again, I PowerPointed you without sharing it, sorry. When it's associated with the feature size, we have that same tolerance zone, but it is now sitting in between the center line of the part itself. I'm going to try something different here and see if I can't share some stuff on here. Yeah, right, it's showing up. So this line right here is the center line of the part between these two faces. these really super straight lines that I drew on the iPad represent the tolerance zone around that center line. But if you notice, one of the big differences between the directed to a surface versus directed to a feature of size is we have this modifier on here. And the reason for that modifier is we have a, let's see if this works now too. Not on center there, but our tolerance zone is this circle right there. And the diameter of that circle is equal to 0.02 inches. And one of the big things that ends up happening is the difference between the left tolerance zone and the right tolerance zone is our left tolerance zone is really a two-dimensional tolerance zone. Our tolerance zone on the right side is now a three-dimensional tolerance zone. So any of the center line of that part has to fall within that circular tolerance zone for the entire length of the part. If it does that, we've got a good part. So it can go up and down, left and right, angular, sideways, whatever. But as long as that movement stays within that center line, that circular tolerance zone, we have ourselves a good part. So the part can be a little bent, it can be a little crooked, it can be a combination of both as well. Cool. Oh, look at that. Now I'm going to erase that there. New trick I can do now. So went through this piece already, this piece. So we also have the ability to use maximum material condition. The interesting thing about maximum material condition is rule number 1 becomes overridden when you apply a modifier like maximum or least material condition. The straightness tolerance value may be larger than the feature size dimension tolerance. The diameter symbol must be specified, and the tolerance zone is a virtual condition boundary. Kind of forget about that last piece, but let's go back to this slide again here. Let's see if I got a different one. Sorry if I'm making you sick jumping around here. But using that, let me go back there. So if we were to take this tolerance zone and we were to rewrite this feature control frame to having a modifier on there. So straightness within diameter of 0.02, M with a circle. Wow, that's horrible. Let me try and redraw that. Straightness, a diametrical tolerance zone of 0.02 at maximum material condition. So based on everybody's homework, what is maximum material condition of this diameter?
12.7.
12.7. So 12.7 is maximum material condition. So at 12.7, our straightness tolerance, oops, what did I do here? Our straightness tolerance is, sorry here, 0.02. I'm going to do a little here. So here's our tolerance. Here's our size. And the reason being is this pin is going to fit into something else, right? So when it's at its biggest size, it has to be at its straightest feature or straightest form. But as that part gets smaller, we're allowing it to be less straight. So for every 0.1 of a millimeter that it gets smaller, we could add that 0.1 to the tolerance zone. I'm just going to skip over here. All the way down. And I'm running out of room, but all the way down till we get to the 12.2. And that's what we call bonus tolerance. So the maximum material condition gives us a little bit more tolerance the less we get away from that maximum material condition. And if you think about it from a, let me turn off my screen share here, go back to my camera. So if you think about it as this pencil that I'm holding in my hand, if that pencil has to fit into an assembly that's got a hole in it, that hole is going to be a fixed size as well too. And if the smaller that pencil is, the more bent that the pencil can be, and it can still assemble with that component on there. That hole stays a fixed size. So for every 0.1 millimeters that the pencil gets smaller, I'm allowed 0.1 millimeters worth of bend, because it'll still slide into that hole and mate with its assembly. So that's the nice thing about the maximum material condition. The bonuses that we get allows us to have a little bit of flexibility in our manufacturing methods, but it also changes the way that you approach your tolerances from a manufacturing perspective too, because if you have, in the case of like a Scott Forge, they were a raw material producer, our mindset is always to leave extra material onto the parts because of the fact that somebody else will typically remachine the components afterwards. But if we have GD&T on there, sometimes we're doing ourselves a disservice, and we have to hold those surfaces or tolerances are considerably tighter to each other because we're doing that. So it's something that we're working with people on to help them understand what that bonus tolerance does, but it's not an easy concept to get. Back to this here again too. Anybody have any questions on that bonus tolerance? Nothing? All right. Let me skip back here. So the last one we're going to do tonight, oh, I don't think it's the last one, but sorry, one more after this, circularity tolerance too. So we looked at flatness for a flat plane, straightness for a line. Now we're looking at circularity. And if you kind of notice most of these, well, circularity is a 2D tolerance that we'll talk about here as we move further along. Circularity, also known as roundness of the part, is a condition when, for a feature other than a sphere, all points of the surface intersected by a plane perpendicular to an axis are equidistant from that axis. So that's the very technical term for basically saying slice the cylinder and you can only measure the 2D portion of the cylinder. So a cylinder is a 3D form, correct? It's got X, Y, and Z. It's got features extending out in all areas, but circularity is just a slice of that cylinder. And all we're looking at, that's where they're saying it, intersected by a plane perpendicular, that's the slice. So take a saw cut, and how circular is that surface where you're taking that saw cut at. You can measure circularity on a sphere as well too, but again, it's a slice of that sphere. What does a tolerance zone look like for circularity? So it's the space between two coaxial circles. So coaxial means that they share the same center line. So what does a circularity tolerance zone look like? So let's take a look here. So the drawing shows a circular tolerance. Here's our feature control frame. The way we would call this out is circularity within 0.1 millimeters. That is applied to this diameter of 10.6 plus or minus 0.4. So the interpretation of that is that we have a tolerance zone that is two circles that are 0.1 millimeters apart from each other. So that distance between here and here is 0.1 millimeters.
But that would make something awful sloppy if it wasn't, because if you're making something to fit something and it's got a tolerance, I was watching a video today, so you know, so if you in the video, this guy shows this part and it has a tolerance of ±4, and and what's going, the dowel is what he was using, is going in the hole and it's got a ±4. By the time it's over with, it could be extremely sloppy if you don't hold it, the tolerance closer, right?
That what you're talking about is a tolerance stack up analysis, and you, as a design engineer, that is definitely part of the process that you have to go through. So what you're talking about, Dave, is if we, let me pull out this, I'm going to go back to the whiteboard here. So if you had a pin that was 4 inches ±0.1, and then if that pin had to fit into a hole inside a part, and the design engineer, I'll put the diameter symbol here too. Yep, that's pretty ugly. Put the same tolerance on the hole as on the pin itself. What you can end up with is, if two different people make this part and they don't know they're going to go together, this one could come out at 4.1, this one could come out at 3.9, and when you try to assemble those two components together, that pin is not going to go together in that hole very well. If any of us have ever bought a piece of furniture from Walmart or Target or IKEA, I guarantee you've run into this before too. But so what we call that is a tolerance stack up analysis. And as a design engineer, there's firms that'll do this for you. So imagine if you're designing an automobile and you're looking at all those components that have to go together into that automobile. And you have to look at pin sizes, hole sizes, you name it, to make sure that everything is going to fit together properly. Not only that, you have to worry about, by the time you stack all these components up together, is it going to be taller than the, let's say you're building the engine, is it going to be taller and won't allow the hood to close on the engine? So all these things that you have to look into, but you run into the same issues with GD&T from a stack up standpoint too, Dave, where if you said that this 4.1 had to have a circularity of 0.2, and then you came over here and said this hole has got to have a circularity of 0.4, and you want that pin to fit pretty snugly inside that hole, there's a chance that the hole is a lot floppier than the pin allows, and you're not going to be able to assemble it. Every time you flip it over, it's going to fall out, right? So it's pretty interesting, because in a lot of cases, if you think about for General Motors or Ford, it's not the same company that makes every component on the engine that goes into that car. So if you're not paying attention to what your tolerances are when you're designing that and how everything's going to fit together, once everything finally shows up, you're going to run into problems. You won't be able to assemble the component. So go back over to here for the circularity. But yeah, so defining what that tolerance is huge. For this class, you know, when we get to our final exam and things as well too, I'm more concerned that you understand the symbols and what the tolerance is than I am about whether or not it's too sloppy for the application. We're not going to worry about too much in depth in the application, because I couldn't tell you if 0.1 is a good tolerance or not on this part. It might be. It could be very sloppy for a pin that's going to hold your piston head to your I forget the name of it, but the hold your piston together in your engine, but it might be super loose for the dowel pin that's going to be holding your target nightstand together. So it's dependent on the application is going to determine how tight those tolerances need to be. But in the case of circularity, what we're looking at here is that the tolerance zone of 0.1 represents two coaxial circles that are 0.1 apart. And if you notice, it goes all the way across here. Rule number one applies to circularity. So again, the tolerances that we give, in this case, 10.6 plus or minus 0.4, you can't make the part at 11 millimeters and then have it out of round by 0.1. Can't go, the surface itself can't go greater than 11 millimeters on the part. So that rule number one definitely limits circularity deviations to within the size limits of the diameter. So in this case, your circularity is, without this tolerance on here, it's got to be circular within plus or minus 0.4 millimeters. What modifiers are allowed on circularity? Again, this release the restraint requirement F or statistical process controls. Those are the only two modifiers that are allowed on circularity. How do we specify it? By applying it to a surface. So you can look at the left view of the drawing and you can say circularity to this surface within 0.3. You can put an extension line and apply the circularity to that extension line, or you can apply it to the front view of the drawing to that same surface. So all three of these represent the same tolerance, just shown differently on the blueprint. Standard compliant, we do our care test again too. We check for datums, we assess the application, we review the modifiers, and we evaluate the tolerance. Where would we want something to be circular? So obviously things like rolling characteristics. If your tire or your wheel on your car was not round, it'd be a bumpy ride. Sealing surfaces, again, think of a hydraulic piston as it's coming in and out of its assembly. If that wasn't circular, when it's passing through the gasket, we're gonna have oil leaks. Appearance, once again, it might be a bit more wide open of a tolerance for an appearance tolerance, but it's still there. And then bearing applications. Circularity can be applied to a cylinder, typically is, but again, circularity does not override rule number one. If rule number one applies, the tolerance value must be less than the associated feature size tolerance. So just again, saying that no feature, that rule number one, that plus or minus 0.4 that was on that drawing before, that is the maximum size that part can be. If we produce the part at the high limit of the tolerance, it's got to be perfectly round. If rule number one does not apply, which I don't know when it would, so I don't know why I have this on here, the tolerance value may be larger than the size tolerance. And the tolerance zone is spaced between two coaxial circles, as we showed earlier. And the distance between the circles of the tolerance zone is equal to the circularity tolerance value. So in our case, it was 0.1 millimeters between those two circles. So we move from circularity to cylindricity, and if circularity is the 2D brother to cylindricity. So if a circle is a 2D feature of size, where a cylinder is a circle is a 2D feature where a cylinder is a 3D feature. We'll talk about the differences here in a minute too. So cylindricity is the condition where the surface of that entire revolution, all points within that revolution have to be equidistant from a common axis. So the center line. Cylindricity tolerance is the tolerance that defines the deviation permitted on that surface. It applies for the entire length of the cylindrical surface simultaneously. That's the big key, is the simultaneously. Circularity is independent of each other. So you can have features at the top of a part check more out of round than features in the center of the part. When we're talking circular, they're independent dimensions from each other, where cylindricity applies across the entire part. So it tends to hold things a bit tighter as well. The tolerance zone is the space between two coaxial cylinders. So those coaxial, again, means shares the same center line. Applies to the entire cylindrical surface, and the diameter is established from the tolerance cylinder. The distance between those cylinders is the cylindricity tolerance value. Rule number 1 applies to regular feature size. Cylindricity deviation is restricted, right? So again, same just thing like circularity. If we're going to have a tolerance on the part, on the example of 10.4 plus 0.2 minus 0.2, if we're holding it to the high size, then the cylindricity has to be perfect. It has to be perfectly cylindrical for the entire length of the part. Where rule number 1 applies and the cylindricity tolerance is specified, cylindricity tolerance must be a refinement of the size tolerance. So again, just can't be bigger than what we're, rule number 1 is creating for us. Let's take a look at rule number 1 and cylindricity. So 12.8 to 12.0 millimeters on the top part for this pin that we've got drawn. This is the rule number 1 tolerance. So there's no cylindricity applied to this, but still the part has to have a cylindrical tolerance, right? Everything, all points have to lie within a certain area. So that tolerance created is this 0.8 between the two coaxial cylinders. But taking a look at what this part could look like and still be considered good is this triangle shaped part in there. So they're showing that this 12.8 circle on the outside is the maximum material condition of this dimension right here. And the 12 millimeter is the least material condition. Sorry, where they show that? Oh, it just shows up funky on here too. This diameter 11.2 is the actual cylinder that fits in here. So we're showing a pin, but if this happened to be a hole inside the part and we follow this 12.8 to 12.0 rule and made the shape not necessarily round by machining it in a weird method or putting it in a weird method, the designer is saying, hey, I need a 12 millimeter pin to fit in here. Based on this shape right here, the largest pin that would be able to fit in is 11.2 millimeters. Wouldn't work. Modifiers that are allowed, again, only that feature which releases the restraint requirement and statistical process control requirement. Two not so common modifiers to be placed on it. How can it be specified? Very similar to cylindricity, or I'm sorry, circularity. So leader lines on the left view drawing to that surface, extension line, or to the surface on the front view of the part too. Standard compliant check again, looking for datums, assessing the application, reviewing the modifiers, and evaluating the tolerance. Cylindricity applications are just about the same as circularity applications. You want a round feature on the part, so you're going to specify cylindricity or circularity. And again, it just depends on your application, which one you choose, circularity versus cylindricity. Circularity is going to check just a 2D section of your component. Cylindricity is going to check the entire feature. Circularity is a little tougher to check because it is checking a two-dimensional section of a three-dimensional part. So in the case of our experience here at Scott Forge, we're using portable arm coordinate measuring machines. Those machines will not check circularity because we can't pin them to a 2D profile. They have to check the 3D profile. So the only thing we can check is cylindricity at that point. Cylindricity tolerance applied to a cylinder. Cylindricity tolerance does not override rule number 1. If rule number 1 applies, the cylindricity tolerance must be less than the associated feature size. The diameter must also pass through its maximum material condition boundary. So once again, if we're going to hold all the way to the high limit of the tolerance, it has to be almost perfect form or perfectly round at that point. Rule number 1 doesn't apply. The cylindricity tolerance may be larger than the associated feature size dimension tolerance. So the tolerance zone is the space between two coaxial cylinders, and the distance between the cylinders, the tolerance zone, is equal to the cylindricity tolerance value. I may, when I said before, I'm not sure why rule number 1 may not apply. It can not apply in a case when we would put down something called a basic dimension. I don't know if those of you that just recently took your blueprint reading course, a basic dimension on a print shows up as a, if let's say we call it this diameter here, and we were to say it's 12.4, and you put it inside a box, that means it's what we call a basic tolerance, or basic dimension. If you find a basic dimension, you have to find the GD&T that's associated with that basic dimension. So in this case, we would have a cylindricity call out of 0.2. Sorry for my bad drawing again too. So that would mean rule number 1 doesn't apply and the GD&T does. We can also draw that part to look like this and say 12.4 plus or minus 0.2, have that same call out for cylindricity, and the feature of size is going to control us from a rule number 1 standpoint, but we still have to be cylindrical within a certain tolerance. In this case, since the dimension is basic on the left side over here, we end up having no rule number 1 apply there. Any questions? That's it for boring you guys for tonight. So again, reading that book and doing the few homework assignments that are due next week are really going to help out and further us along. I am going to take a look and see, since we're not able to be together in class, to see if there's some additional resources or some reading. I've been trying to find some articles too. GD&T is super popular out there, so you can't find everything, being sarcastic. But there's not a ton of documentation out there for it, articles, videos, or anything to read is significantly more technical than we're talking about here too. So I'm going to stop the recording right now.